What's up, everybody? Welcome back. Today we are working on our collaborative Rube Goldberg machine. So this idea stems from my childhood. When I was a kid, we went to this place called Science World in Vancouver, Canada, and outside this building was this like really fun contraption where there were these like kind of like pool ball sized objects in this like contraption, and it would like kind of they would go around this system. There were like conveyor belts, there were like funnels. It was just kind of fun as a kid to run around and like watch these things and figure out like how it's going to get to the next spot. Like, is it going to run into another ball? That would be very exciting. All that type of stuff. And so like this like idea is like burrowed itself deep into my brain, where it's like fun to watch the thing move, you know? And so what I thought would be kind of fun is if we could build some sort of like virtual version of this, where the ball goes through environments that are like super scriptable, right? So I'm kind of thinking like maybe we have some chambers, right, that are all kind of like stacked together, and each chamber is defined by some like plugin, right? I guess that's what we'll call it. And maybe your plugins can be or do some like pretty advanced things. So like we have like a ball and it's coming in over here, and maybe we have like one room is like it's got like a planet in here, and the ball is gonna like orbit around the planet and then shoot itself back out. Maybe in this one there's like a wall and like a cannon, and the ball falls in the cannon and the cannon like fires it out like this. Maybe in this one there's like a pool of water, and every once in a while the water gets like siphoned out and the balls kind of come with it. I want to like allow for freedom for like super customizable environments. And then what I'm thinking is if we were to make these like WebAssembly plugins, these things are like should be pretty sandboxed to the point where I wouldn't feel too uncomfortable allowing like user submitted environments that are like super customizable, right? So that's kind of like the overall plan. Something like server sits somewhere, runs a simulation long term, shoots balls into these environments, and the environments are like coded by users. And over some amount of time, we might see some sort of like interesting behavior, right? Like imagine you have one chamber that kind of like eats balls, and over time, like over like a day, you end up with like a bunch of balls stacked up in here, and then it hits like some threshold, and you could like look at the you could like watch this chamber and go like, oh sick, it's about to fill up, and like over time you see it and you get that like nice little release where like all of a sudden this flap opens and they all shoot out into the next chamber, whatever. So some server runs simulation over long term, some client views simulation at this state, this point in time. People can upload environments for part of the simulation. And we're on day 2 of this project. I guess technically maybe you could argue it's day 4. We did a couple days of like WebAssembly investigation to make sure that like the idea would work, and I think it will. And then yesterday we actually started coding up just like the basics of physics. So we built this web server, we dropped this ball, it bounces off the floor. That's as far as we're at right now. And so the idea is if we have to flush out our physics system, because we want some form of consistency between these guys, but obviously you can tell from these like examples here, like something like orbits, something like cannons, something like water, like all of those are gonna have to like adjust the physics system pretty heavily. But I think that we still want some form of consistency between the chambers. So I want to flush out like just the world's shittiest physics system first, so that we have something to work with. Then once we understand what goes into a physics system, then we can start working on like the APIs for how a environment would be allowed to alter that physics system, right? So we have this really rudimentary simulation, and what I want to work on today is just getting like any form of collision working, right? So right now he's only checking if he goes like out of bounds of the whole world, which is just this like little box. I would like to define an object, have the ball hit the object and bounce off it appropriately. Then maybe we can try to have more than one object. That would be crazy. Multiple objects? Wild. And then once we have that, maybe we can try kind of throw in like multiple balls and stuff. Yeah, so I think that's the plan. Full disclosure, I have no idea what the hell I'm doing, right? So don't think when you come in here you're going, why the fuck did he do it that way? A good and likely answer would be, I don't fucking know, right? So let's just keep that in mind as we move forward. Okay. So we are at 4 minutes and 40 seconds into stream. So hand wavy, I don't really know what makes sense here, but let's say just hand wavy. We have platform, right? Ball moves, hits platform. I think that what I've like kind of seen is that generally you just kind of step your physics system at like short intervals. Let's think about what I'm going off here. I'm going off some Mario 64 videos I've seen where people talk about quarter steps, and I'm also going off my intuition on how I've seen Blender work, right? So Blender has like this like physics simulation thing in it. And if I remember correctly, there's like this concept of like substeps somewhere. Maybe it's if I think I have to enable physics on a thing. Say that this is a rigid body thing. Maybe it's over here. Somewhere you say, hey, I want my solver to run at like this frequency. And I think that if your solver doesn't like check enough subsections of something, if say you have like, you know, a box and another box here, if this box moves like this far in one step, it will just like fly right through the thing, right? So I'm kind of going off this intuition, as well as like kind of like degenerate behavior I've seen in video games where like you see like things run into each other and then like explode. I'm just kind of like building a mental model based off all of those things. And what I'm assuming is that ball moves in like steps. Eventually they check for collision in this thing, and if this is inside this thing, they like push it out, right? Hand wavy, I'm also thinking about how if you were to bounce a ball off a surface, if you like the physics of this, I think, is that you're going to lose some sort of like horizontal velocity to friction, and you're gonna lose some sort of like vertical velocity from like loss of energy. So I think the reason that the ball bounces, if I understand correctly from like the Wikipedias I've been reading the past couple days, is like the ball hits the ground and then it like kind of like squishes a little bit and then it like unsquishes, and this unsquish applies like a force to the ground, and the ground pushes back up, and then the ball goes up. So if this thing's like perfectly elastic, then it will go back vertically the same amount, like at the same speed that it came in. And if there's no friction, then it will continue horizontally at the same speed that it came in. Hand wavy. It should never go faster, right? But it should do that. So I think with all of that in mind, we can think about like a thing on a slope. A ball come in like this, right? And I think that the wall has to push back out in this direction. And with no friction and no loss of energy from elasticity, it should keep the same speed, which kind of means that it just does like a perfect like ball come in, ball come out at this angle has to be the same as this angle, right? I think that if we lose some energy due to elasticity, I think that this angle shrinks. That's my guess. People on stream yesterday were saying that the angle that comes in should be the angle that goes out, but I think I don't believe that. Because if the wall can only push in this direction because there's no friction, if there's no friction, it can't move it sideways, then it has, like, the loss of energy has to be in this direction. So that means that this angle would have to shrink. That's my guess. But what the fuck do I know? Right? I know nothing. So, let's start by assuming perfectly elastic and no friction. And we'll start with an object that's completely horizontal. I think that what we want to do, is in this scenario, we're essentially mirroring over this direction. Is the ball rotating? That's a good question. I'm kind of assuming that either it rolls perfectly or it slides perfectly. One of the two. We're kind of modeling the ball right now with no upwards direction. So the ball doesn't have like an internal rotation to it at this point. So I think that we can either imagine that it's perfectly sliding or it's rolling and the friction is like, it's perfectly converting its like angular velocity into non-angular velocity. But I think I'm just not going to think about that right now. Because also, we want to keep the model somewhat simple, right? Because, like, it doesn't matter, right? We just have to get, like, something that's, like, a little bit sane so that it doesn't look like shit when we look at it. But it doesn't have to be perfect, right? It just has to look reasonable. So, we don't have to worry too much about it. Okay. So what I was thinking is ball come in some velocity, ball go out some velocity. Maybe using vertical actually isn't the best example. Let's do it on an angle. And we'll do shallow angle. Ball come in, ball come out. I think effectively what is happening here is, let's see. How do we draw this so that it makes sense? If these are like velocities, right? And these vectors, right? If you can imagine like some time step, these are gonna be the same. And if you like just kind of like take, can I do a free form select here? If you just like take this guy and shove him over here, what you end up getting is you are flipping him over this axis, like this line, I think. Or you can also think of this as this triangle with the normal vector. He's basically going to double this distance, I think. So I think that what we can do is if we have normal vector here and initial velocity here, we're essentially looking for this side of the wall. And if we look at the projection of this guy, if we take like the roots of these guys and line them up together, I think that turns into this triangle, right? This way and this way. Sorry, let's make sure that we have the angles correct. Maybe we'll do this by dragging this up here. And I think that ends up being, we can like, if we do the dot product of this guy, we get this distance, I think. And so, because the dot product is like the projection of one line onto another, right? If you have like this vector and this vector, your dot product is like this, which is also AB cos theta. But I don't think we really need the angles here. I don't think. Right? Because if we just take this projection, we're going to have some distance along the normal vector. And I think that we can just adjust this, our like initial velocity, by 2 times this projection onto the normal vector. I think. That's my guess. We'll see if that looks like absolute fucking shit. But I think that's where I want to start. Because then once we have collision with once we have like adjusting with some normal vector, we can then put an object that just has like a line and a normal vector somewhere, and we can say like, did we hit this line, and then apply the change. So I actually think I'm going to change this first step from collide ball with object to collide with handle non-vertical collisions. Right, because right now we only collide with the ground, and our collision math here is like just assuming that we're only checking if we're like below the 0 line, and then we only handle vertical bouncing right now. So I think I want to change this to use like the floor's normal vector, and then do this calculation, and then see if we like kind of bring the ball in at an angle, if that still does something sane. You know, that's, I think, step one. Okay, so our physics simulation is running in this thread where every time step, which I've got at 1.6 milliseconds for now, because it started at 16 milliseconds, which is 60 FPS, and then the simulation was a little unstable, so I just deleted a number. That's how we ended up at 1.6 milliseconds. It doesn't really fucking matter as long as it's like small enough step. Also, this isn't technically 1.6 milliseconds, because if this takes some amount of time, and then we're just like kind of unconditionally sleeping for some other amount of time. So it's running at some frequency that's close to 600 steps per second, but not perfectly 600 steps per second. Something a little less than that. Every amount of time, we run our simulation with some time step. So we say this is how much time has passed between this time we ran and the last time we ran, and then we apply gravity, we clamp the speed. For those of us who were watching yesterday, I was attempting to do like max speed by using drag. And that drag was causing like behavior that I didn't like. I think that I wasn't applying the drag formula correctly. And then I realized the only reason that I cared about drag to begin with was because I didn't want the ball just accelerating forever. So I've replaced drag with just like making sure that the ball never goes above 3 meters per second, which is fine for now, right? We are big fans of just not doing a lot of work. Just doing whatever is good enough. Good enough is our slogan. Then we apply the velocity of the ball, and then we check for collision with the ground. And so I guess here we are going to be adjusting our collision with the ground check with collision with some object that happens to be on the ground. Yeah, let's start there. In which case, if that's where we're starting, then we should actually change this to go back to collide ball with object. And the object that we're colliding with will just happen to be the ground. Yeah. An angled wall will have gravity affect the reflecting trajectory of the ball. Yeah, I agree. But I think that that will just naturally apply itself later on the next step. Because the next step we will always... I think like at the instant that we collide with the wall, gravity is not a factor. We would just have to conserve energy with like how it hits the ball or how the ball like projects itself out. And then on the next physics step, we will apply gravity again. So I think that it's fine. I think we don't have to think about it. That's my guess at least, but we'll see. Okay, so we're gonna have some like ground, and he's gonna have some sort of like some sort of surface. And the surface is going to be modeled as like a line, I guess. So here we'll say that we have a line that has 2 points, I guess. Okay. And so his like x position is 0 and y is 0 because we've set our coordinate system so that the bottom left corner of the world is 0, 0. And then we will do our b is y0 but x1 because the bottom right corner of our world is 1, 0. Yeah, and I guess we can kind of infer the normal of this line based off of the direction of A and B. Does that make sense? Let me think about this. So if we have like A to B, we can kind of assume that this is like a clockwise surface, right? So the normal is here. So if we have A and B, then it points this way. And if we have A and B, it points this way. Yeah, I think that makes sense. I think that if we can encode the normal position out of these 2 points by their order. So I think that's fine. In which case, we kind of can just model the surface as a line completely. Because in 2D, a surface is a line. Which I think makes sense. I think that makes sense. So I guess our surface is going to have A, which is a position, and B, which is a position. Okay. Okay. And now we're going to have to get its normal somehow, which is going to be a vector, which is very similar to position in that it's got 2 numbers, but I think semantically they're different enough that it's worth calling them something else. Okay. So we're kind of saying that we're assuming clockwise direction. So we're looking for something that is orthogonal to the line between A and B. So we're just kind of looking for if we have, let's draw it out. So we have, if we do B minus A, B, A, we should get this vector, A to B. And what we're essentially looking for is a 90-degree rotation from that thing. Normalized at length 1.0. So I guess we could just do... there's probably, like, I think that there's probably some encoding of a rotation matrix that makes this really simple to calculate, actually. It's probably all 1s and 0s, right? In this case, you have 1.0 on x, and this just becomes 1.0 on y if this distance is 1. Right, so you just flip them. If you have this, okay, let's say you have something that's like really small x. You can, like, definitely these 2 distances are the same, and these 2 distances are the same. So certainly you can just like flip x and y and then apply negatives and positives in some intelligent way, right? So probably you'd look at your like what's your rotation matrix? It's like cos, sine, negative sine, cos, probably. And so these just become 1, 1, negative 1, and 1. Probably. Somebody's linking how to calculate normal. Dude, look at that. We've defined, well, what is dx and dy? Suppose I have a line segment going from x1 to y, from 1 to 2. Yeah, okay. I think we got there. This is like essentially what I said, right? So they have, one is negative y times x, or the difference between them, which is what we were talking about. So we have I have negative x times y and x times y. So I was a little bit off. But I think because he has his negative. Oh, is it one of these also has to be negative? Is it like, I can't remember. Let's look up rotation matrix. Where the minus sign is depends if you want to go clockwise or counterclockwise. That also makes sense. Yeah, so this is. Oh yeah, okay, I was close. Okay, so what is like sine? If I'm trying to go counterclockwise, that's positive angle, right? Hand wavy. This is positive y. This is counterclockwise. So I said that I was encoding clockwise direction of A to B, which means that we want our normal to go counterclockwise from the vector of A to B. Yeah. So say B sub A. V is this. And then we just want to invert. The new x position is return. X is cos 90 is 0 or 1? Cos 90. Cos pi over 2. 0. Okay, so we just have, this is 0 times something, so this is negative, our new x is negative y, and our new y is x. Is that really it? Did I do this right? I feel like... right, because cos 90 is always 0, so these two elements cancel out, and so it's just negative y times 1 and x times 1. That lines up with what I was initially guessing from flipping y and x. Let's just make sure, we'll just like do a couple tests. So if I have, 0.3, 0.6, this gives me x is negative y, so this is negative 0.3 and y is 0.6. And then I do another 90-degree rotation. And this becomes, scroll down to the answer for Stack Overflow, but I don't want their answer in Stack Overflow. But it is what I said. But I do want to just double check it. So this is 0.6, I rotate, so now my negative 0.3 stays negative 0.3, but it goes to y. And my 6 becomes negative 0.6. Yeah, okay, that all lines up. Cool. I know I could have just Googled it, which we kind of did, but it's kind of fun. It feels like fun to derive it ourselves. It's like a little bit fun. A little fun. Okay, so now we have the ground normal is equal to ground normal. Boom. Using brain is always better. Hey, let's not get ahead of ourselves. We always try not to use our brain on this channel because using our brains is for nerds. So we have to be careful. Because we're inconsistent, we have to be careful with our words so that we say that it's fun to derive things but not using our brains. Okay. So were we saying before? We were saying something about how the movement is the projection onto the normal. So if we have normal like this and vector like this, we project here. And so we project, invert, and then multiply by normal, I think is what we said. So we say we need a dot product. We don't have dot product right now, but it's easy to make. Function dot. A is a vec2, B is a vec2. And we get a float out of it. And I believe it's just A times A plus B times B dot product. Pretty sure, but I don't want to be embarrassed when I really badly fuck it up. But it is just A times A plus B times B. So A dot X times B dot X plus B dot Y plus times A B dot Y. There we go. Okay, so now we can say that we project our velocity onto the ground normal. Oh shit! Wait. We fucked up here. We want this normal to be 1.0, I think. So we want to do var v divide equals v length. But we don't have divide equals. We have to do v is equal to v div v length. And I know somebody at some point said that we could use the built-in vector instructions, but I didn't do that yet, so we're just doing it like this. We only have mul, so I guess we could either implement div or we could just go 1.0 over. And then not implement div until later. Okay, so now our normal should be guaranteed to be 1.0 because we multiply this by the line. Yeah, pretty sure. And so now this is a normal, and so when we dot our velocity with the normal, we get const movement is equal to this times 2. And then we can't really just say negative. Oh, we can say negative. This is a float. So we say const projection, I guess. Vel ground proj, I guess, is like a name we could use for that. Magnitude. Velocity, ground, projection, magnitude. I'm sure there's some math word for it, but I don't know it, so this actually makes more sense to me than whatever the math word is. And we just multiply that by the normal. So we say ground normal multiplied with the negative velocity this thing times 2. And this should give us like the velocity adjustment. And then we just take the velocity adjustment and add it to the ball velocity. So that kind of handles this. Oh, times our damping factor. Because our ball is not perfectly elastic. How often are you streaming? Most days. Almost every day. I probably I'd stream like 6 out of 8 days, probably, which doesn't line up with weeks, which is kind of annoying in some ways. But I also feel like I don't want to take, like, if I want to stream, I shouldn't force myself to take a break just so that it lines up with the week, and I shouldn't force myself to work extra to line up with the week. So approximately 6 out of 8 days, something like that. Wondering why Zig over Rust? Just because, like, I like it right now. Is about the extent of it. I think, probably, I've said this before, I think, but I'll say it again. I think that if I were to start a company, I would still want to work with Rust. I think that when working with a lot of people of varying skill levels, the, like, floor that Rust puts on your code in terms of, like, I'm not gonna say quality. Quality is the wrong word. But in terms of, like, ability to fuck up, like, the floor is very high, right? So you have a pretty strong guarantee from the language that you're not going to create like a certain class of bugs. Great. And then also, like, the Rust developer community is like super into like strong APIs and zero cost abstractions and stuff. So it's kind of like the direction that the whole language pushes you in is like, if I want to use somebody else's code, I'm confident in it more than I would be in other languages, right? But when I'm writing by myself, I don't feel like I need those guarantees, right? I'm happy to just like fuck around and do what I want. I'm happy to break stuff, right? If something's seg fault, I don't go, fuck you, coworker. I go like, oops, my bad, right? And so like, because of I'm in that environment right now, like taking the shackles off and just being able to like fuck around and do what I want feels better right now. So that's why I think. I mean, it's hard. I think that like when you motivations of people are often expressed incorrectly, right? I think what happens here is like I write Zig and I go, ooh, I like, right? And then I like reverse engineer a reason from that. But the reverse engineered reason is often wrong, right? I think that often if you ask someone why they did something, they will not give you the right answer. Because if you like, I've talked to people, maybe this is a me problem, but I find that when I talk to people and I try to build a mental model of like a person so that I can predict their behavior, which is like a crazy thing to do, right? But I do that. Often what they say their reasons are do not result in good predictions, but what I think that they're actually meant, what they actually did is like a better prediction. Sometimes, if I'm right. Often I'm wrong, right? But like, I don't think that people know why they do things, myself included. I think I forgot to thank Steve O for the tier 1. Appreciate it. Okay. So here we applied velocity adjustment, but we also have to like resolve the collision. And so I think we resolve the collision by just looking for where did we intersect and push along normal until intersection resolved. This is like not perfect, right? You can imagine, like, say we have a ball and he's going into the ground and he's like gone some amount into the ground. If we kind of like just kind of push him back to here, that's not great. But like if our time step is small enough, that like incorrectness shouldn't matter. But is there something that we can do that's better? We could just look at where he is in the object right now and push him along the normal until he's out. That's probably easier to calculate, slightly more correct. We'll lose some energy by doing that, right? Because the ball should end up this distance out of it. Oh, we can just do that. Yeah, let's just do that. We just see how far into the wall we are, and then push it out by that amount. Because, yeah, I think that lines up. The damping factor won't be applied immediately if we do that. But that's okay. We want to do ball velocity equals ball velocity mol 0.85 to apply our damping. And so yeah, all we have to do is just adjust this position. So ball pause. I guess we need to see how far past the thing we are. So how do we do that? We have some line and we have ball and we know that our normal is this way. So we just want to see where the ball would have collided, which is like the farthest point away from the wall. Yeah, we just compute this distance, I guess. Yeah, that seems easy. Do you know some of the cons of Rust? Because it looks like a great tool for everything, because it's high and low level language, but also mem-safe. I'm a Ruby dev and I feel the pain in the ass. I picked the wrong lang. I don't think that like, I mean, I haven't written Ruby, but you know, I guess languages can get in your way, and there's a reason that I'm using one language over the other. But in reality, I wouldn't worry too much about like missing out. That's kind of my opinion on it. Like, for the most part, you can express things, right? Like sometimes you write your Python and then you go like, this is slow and you need to drop down into something else. But in terms of like your ability to make things, like I don't know, it's all the same, right? Like every language has its trade-offs, but like Rust is like, you're right that it's pretty good in that it has like high level and low level performance with high level APIs. That's definitely true. But it is painful. You can't compile things very easily that don't follow its memory model, right? So an obvious example is like thread 1 is like thread 2, and you're like, I want thread 1 to like initialize some global data, right? Global. And then I know because I wrote the program that thread 2 is not going to try to use it until after it's been initialized. And you could even go crazier and you could say, I know that thread 2 isn't even going to exist before this global has been initialized. And with those two constraints, you can make your global, you could be like, okay, I have this global variable, but I don't need to mutex protect it. I don't need to put an atomic around it. That's something that I might do when I'm writing Zig, which is like, error prone and like bad for all sorts of reasons. But if you're just trying to be like, fuck, I just want to see what it's like to try this experiment, and like I need thread 2 to have some data over there while I'm doing that experiment. You can't express this in Rust, right? Instead, you need to like mutex protect this thing and like properly send like your pointer to things over. It's just you have to like deal with all of these like borrow checker and mutex protection stuff that aren't the problem you're trying to solve. And often you end up in this case where in order to experiment with an idea, you have to like properly implement the feature. Where properly implementing the feature is great because like you'll end up with a code base where you can't your final solution will be very good, but it sucks when you're just trying to like jerry rig some shit together, Okay, what we're doing, we were trying to push a ball out of the thing, so we say how far have we gone through the wall? So we have point A and we have point B and we have line between them. We have normal. And surely there's some way to see how far into this thing we are. So I guess we have like our ball, and we want to say at the point that's like closest to the wall, like furthest away from the normal, where does this line intersect with that line? Right? And then when we have that, we can like calculate this distance here and then just push it out by that amount. Yeah. So I think that the tricky part here is figuring out this. And I think that what you can do is if I remember correctly from when I think I've looked at this before for some reason, maybe I just out of curiosity, but I think the easiest way to do this is infinite lines that are not parallel will always intersect somewhere, right? And so you can calculate the intersection of those two infinite lines and then just double check that they're within the bounds of this thing. Yeah, so we just let's think about this. So we know the direction of the line of the ball collision that we're trying to check is the normal. So we have normal is the slope. So the slope, normal y over normal x is the slope plus some offset. And then for this line, we know that the we'll call like the difference between A and B, we'll call it like delta or something. So we can say like delta y over delta x plus b is like another formula. And then the y position where these intersect will be when these two things are equal. So you can say like, let's fold these into slopes. So we can say like, mx plus a is equal to nx plus b. And then this, if you want to resolve x from this, it's just x is equal to a minus b over m minus n, I think. And then you can just check if this x is within the bounds of this. That sounds reasonable to me. Dot a minus pn might be useful. Because Why? Let's think about that. P minus A. What is P and A here? A. Or you? Oh, I guess maybe you can't read my writing. Do you mean like the dot product of, if this is my line, the dot product of A, B, and N? A is 1 point on the line. P is the position of the ball. Oh, yeah. You're right. Let's think about this. One position on the ball. So you're saying like I have this vector and I project that onto the normal, but the projection of this projecting onto the normal will give me this distance, which is how far I am from the line. You're smart. Thank you. I would not have got there myself because I would have done this and then done check. Okay, let's think about this again. And then presumably there's some sort of like negative positive check you can do to see if we're in which side of the line we're on. But I don't know if this handles. Does this handle if we're within the bounds of the line? I don't think it does. We still need to find out. We still have to figure out if we're like within the bounds, which is what this is doing. So maybe we still need this. Thinking. Okay, so I guess I haven't really like fully grokked what the problem is like, so say that our line ends here and here, and the ball falls here. The ball ends up here, and if we take this here, this like the projection that we were just talking about, onto the like the normal, then when we apply that, we will be outside of the bounds of this line. So we can just check. Yeah. We can like do that motion, check if we're outside the line or not, and then call it a day. Seems reasonable. Okay, so ball collision point is going to be the ball center, but we have to offset it by where it would hit, right? So if we have the ball here, we're basically trying to like walk radius distance along the normal of this plane is where the ball will hit, I think. So this is going to be like ball pause sub ground normal times ball radius. Yes. And then we add this to the ball center. Yeah. So this gives us this point on the ball. Then we dot product. So we say that the line, surface, ground, A. We subtract A is here. We're trying to draw this line so we can project it onto the normal. So here if we do A minus ballpoint, then it lines up with the normal correctly. Sub ball collision point. And then we we say const collision resolution distance is this dot product with the ground normal. Yes. Then we say const if collision resolution distance is greater than 0, then we need to push the ball out. So then we can say ball position I guess all of this velocity adjustment also should only be done if we collided. So this kind of goes down here. Yeah. And then the position is just add the ground normal times the collision resolution distance times 2. That feels right to me. Feels right. Now, was there anything else we had to do here? Or are we just chilling? Oh, here we need to actually check if we need to check if after we add this distance, const ball line intersection point is equal to this. So then we can say const collision resolution vec is this. Yeah, the ground normal times the distance. We check if we add this to this guy. If ball line intersection point x is greater than is between A and B on the line. Yeah. So we have to say like let's think. So if I'm trying to check if if x is between A and B, A might be greater than or less than B, so we have to handle both of those. So we can say A dot x is greater than B dot x. I'm pretty sure that I don't have to do this if statement. But I don't really know how else to do it right now, so. We take the intersection point, and we say, if A is greater than B, then we say, x is ball intersection point x is greater than B dot x, and ball intersection point is less than A dot x. Bool collided equals false, or var collided is a bool which is undefined. Yep, here we say collided equals this, and here we say collided equals the other way. Again, I'm pretty sure that there's a better way to do this. I just don't have it in my head right now, so we're just doing this instead. And now we should be able to tell, that will tell us if we collided. Yeah. So if we collided, we do all this stuff. Don't you need the same validation for y too? I don't think so, because for every x point on the line, there is one y point on the line. So I think that if we have the exact point on the line where we collided, then it's fine. You know? I think. Could be wrong. But I'm pretty sure. Reasonably sure. Okay, and then here we just have to add. Here the ball position is the ball line intersection point added with the collision resolution vector again. This is what I believe the answer is. And if we did all of this right, nothing should have changed. But I doubt we did it all right. First of all, it doesn't compile, which is, of course, 220. So this is supposed to be x on both these. And then he doesn't like this addition here at 226. So this has to be ball velocity is equal to ball velocity add the adjustment. Yeah, this seems fine. No add. I can't add two vectors together. What have I done? Okay, fine. We'll implement add because I'm pretty sure there's no reason that that shouldn't be allowed. Plus plus. There we go. Okay. Expected type F32. Ball velocity add. What did I do wrong here? 233. He's saying that when I add this velocity adjustment, which is a vec2, expected type F32. Did I fuck up? Oh, yeah, I did. I did. A and B. Oops. Oopsies. Okay, so now it's running, and let's see just how fucked up it is. That looks kind of right. That looks like what it was doing before. Wow, look at us go. Look at us go. Okay, so if we did everything correct, we should be able to just change our ground object to like kind of be on an angle here or something. And we should be able to see the ball move along. Kind of like bounce off it or something. So let's change our ground. And maybe we should draw the ground as well. That will help. So we will say that the ground, maybe we add the ground as an object in our simulation. So that we can request the ground from our JavaScript API, which is going to be ball. Where's ball? Is that sometimes bouncing off the air? I don't think so. It resets every once in a while, which I think is probably what you're seeing. Let's double check. We can't build it because I added some text. Oh, we'll check in a second. Okay, so here we have is resolution of ball. This is not great, but for now, I don't care. We are going to get the ground, and we're going to respond with the ground, which means that we need ground here. Surface. And when we call this guy, we need to feed him the surface, which means that here we need to extract the surface. I guess we'll call it ground. That makes more sense. Boom, 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 boom. Okay. Now in our index JavaScript, we should be able to get both the position of the ground and the ball. So here we're going to get our ground response. Response comes from ground, and the ground is the JSON of the ground. Response. Did I spell it wrong here? What the fuck? Ground reposnance. There we go. Okay, so then we should just be able to draw a line here. So I think it's CTX line 2, ground B, X, ground B, Y. But we need to convert the ground positions to pixels. So this is just times the canvas width. Maybe get all objects in one fetch. Yeah, that's not an awful idea. But I've already done it this way. So, get fucked, I guess. Can I like set the cursor position somehow? How do I like? Okay, we'll look it up. HTTP HTML canvas line 2. Give me an example, baby. Move to. That's what I'm looking for. So we just go from A to B. Yeah, that seems right. Zig build and run the ball machine. Fuck. Main 299. He's missing ground. Where does that go? That's ground is equal to whatever we specified const ground earlier. Just kind of yoink this shit, slap them over here, and then here we replace const ground with self ground. Boom. No? Apply Gaussian ball and ground. There we go. Let's see it. Wrong page, this one. We do not see that stroked line at all. Should that be y times height? No, everything's normalized relative to the width. Just so that our coordinate space stays square. Otherwise, our y, if we had like our position of everything in here as like 0 to 1y, we would need to adjust our normalized coordinates so that like the space stays square, if that makes sense. But if we just normalize everything relative to width, it doesn't matter that the aspect ratio isn't 1 to 1. Let's make sure that the ground came up correctly. So the response does have 0, 0 to 1, 1, which is great. Let's make sure that we drew it sanely. Maybe set the line width bigger so it's bigger than the border. But I would think that it should be drawn after. So it shouldn't matter. That would have been my guess. But you're right. Do I have to close path here too? Let's look at the example again. They just call stroke. Yeah, okay. So let's do what you suggested because I'm curious. But I don't feel like it shouldn't matter. I feel like it shouldn't matter. Oh. We forgot to invert it, that's why. It's also red. It's also black for some reason. Do I have to reset the fill style? Or, yeah, fill style. Do I have to reset it every time? Like, that doesn't make sense. Why is it black? Strokes. Maybe it's because I did fill style instead of like stroke style. Maybe I made a mistake. There we go. Yeah. Okay, so for the border, I want the stroke style to be black. There we go. That's better. That's better. And then we just need to do, for the ground, we do canvas height minus this. There we go. We got a thing on the ground. And so let's make the ground blue or something just for something else cool. And then let's try making the ground, let's put the ground on an angle and just see what fucking happens. Because there's a good chance that it just does something like fucking stupid. So let's put y 0.5 here and just refresh. Oh, hell yeah! Wait. That's sick! That bounced off the thing! Let's reset the simulation. Before we were resetting, if we didn't see movement for like 10 frames or something. But instead, let's just reset it after some amount of time. So reset after timeout. And maybe our simulation will hold some sort of like max duration. And there's gonna be like some duration in seconds. We don't need this pause history anymore. So this is just gonna be every step we are going to say that self duration, I guess. Calling it max duration is stupid. We want to take our simulation total duration, and the duration is going to have the delta appended to it. Then we are going to call reset after timeout on self. And here it's just going to say if self duration is greater than 2 seconds or something, we do what we did before. Reset the shit out of it. Fuck! 287, we need to change. We don't have this like position history thing anymore. We have duration is 0. Okay. He's definitely not resetting. Let's say stood debug print duration. What did I fuck up? Oh, we also have to reset duration here, I guess. Self duration equals 0. Does that make it work? Oh, wall. Oh, I'm only ever resetting the Y position as well, which is a problem. So the X position, we're just going to set at 0.5, and down wherever we start this thing, we just set this guy to wall start X. There we go. Okay, yeah, okay, and then we'll just change the max duration a little bit. 1 second. God, that's actually so sick. I really did not expect that to be very sane. Let's try increasing the slope of the ground a little more. So here we can make it so that it ends at x 0.5 to make the slope a little bit bigger, maybe 0.6. No, we'll do 0.5 and we'll move the ball start position over to the left a little bit. And then maybe we'll even raise this on the start point a little bit. Oh, but now the ground doesn't exist. But it does look like it's bouncing at like a different angle. Let's also increase the frame rate in our JavaScript. It feels like it kind of like jumps here, maybe, in a way that it shouldn't. But you know what we can do is we can add a second object here that maybe is like makes a V. Can you make the ball slow for a second? That's not an awful idea. We can just change our delta. We can just like 10x slow down and just see what it looks like. Oh yeah, I think that looks fine, right? That feels fine. Maybe the jump was just like from like mutex contention somewhere. Donk. Oh, that's so sick, man. That's so sick. Okay, yes, I think what I'm gonna do here is I'm just going to immediately. Oh my god. Okay, for everybody who's been spamming request animation frame, I did this on purpose. And I did it because I think the polling rate of the server should not be determined by the refresh rate of my monitor. That seems silly to me, right? So if we were no, it's okay, because somebody was spamming yesterday too, and I could be wrong, right? There could be some reason that I should be using request animation frame that I'm not, that I don't understand, but because I am pulling the ball position and ground position every time that we render a frame from the server, it seems silly for that to be like dependent on the refresh rate, right? It seems like maybe if it's to avoid tearing, then it would make sense to how do I say this? It would make sense to like pull the server in like one thread at some interval and render at the refresh rate of the monitor. But also, I think it doesn't really matter right now. So, does the velocity change? I can't really tell. It also looks like it's like getting like jittery the longer it goes on. There's something to look at there where maybe something's not getting garbage collected correctly. Because I don't think my server should be changing. Like, there's no like allocations happening on the server, so I don't see why it would slow down. But the JavaScript slowing down would make more sense to me. But when we, I guess you can also test it by just refreshing JavaScript and not refreshing the app. But the velocity there feels right to me. Maybe you can only draw on reset request animation frame and use set timeout for getting data from the server. Sure, but like why? You know, I would need like a reason to do that because it's like slightly more work. Okay, so let's put the frame rate back to the correct frame rate or the correct simulation speed. And let's add a second wall. We are lazy. We are definitely lazy around here. One of the first jobs I got hired for, my boss told me, he's like, do you know why I hired you? And I'm like, no. And he's like, I hired you because you're lazy. I'm like, that's crazy to say that to me. And he's like, because I know that by being lazy, you will hopefully find good solutions to problems because you're not going to just ram your face into the wall over and over again doing something that you don't want to do. And I'm like, well, that's true, but I don't like that you said it. But I think it is an accurate accurate view. Uh, Unless we do client-side interpolation, there will be literally be zero visual difference. That's kind of what I assumed. That's what I assumed. Okay, so our simulation now, maybe instead of having the ground, we'll just have a collision objects, which is going to be like some sort of like maybe runtime list. Runtime, we'll make a. I guess for now we have no way of like adding and removing objects, so just having it be compile time is fine. Yeah. And then wherever we had ground used before. True but hurtful. No, I think he was talking to me, not to you, about the hurtful thing. Recurniston. Dude, that is only consonants. How's anybody ever supposed to pronounce your name? Okay, so we have one surface, which is the ground. And then we'll just have another surface. Or we shouldn't call it the ground anymore. We'll have the downward sloping one, and then the upward sloping one. So this is going to start at 0.050 and end at y 0.6x 1.0 or something. Okay, and then 301. What's it not like? No field name surfaces. Oh, it's surfaces, not surface. He still doesn't like that? What did I call it? Colliders? What did I call collision objects? Sure. Okay, now he's mad that I'm using the ground somewhere. So here we should be. Okay, so here, when we render these things out, we should be copying out all the surfaces. So surfaces equal to simulation contexts collision objects. I guess we'll call it collision objects. And I think now is a good time for whoever said that we should return everything in one request. I'm on your side now. Because I think this is a natural time to do it. So maybe this, we will say this is some sort of like slice of surfaces, I guess. And then here, what we can do is we can just say const response JSON is some structure. I think we can just do it like this. And then we can say that our ball is a ball. And the collision object is this. And then we just construct this thing. So we say stringify response JSON, and we fill in the deets here. So ball is equal to ball. And collision objects is equal to collision objects. Boom, easy. Okay, Zig build. And he doesn't like that at 70. Here. Right, because we're gonna rename this from ball to like simulation state. Okay. And in our index JavaScript, we're not gonna get the ball anymore. We're gonna get the simulation response is from simulation state. This is the simulation state, comes from the simulation response. And then we just have const ball is equal to simulation state ball, and ground is ground, and then everything else should just work, I think. Except ground doesn't work. This is collision objects 0. Okay. We'll have to render all of the collision objects eventually, but let's just get something compiling so that we can see how it's broken. collision objects here. This guy is going to have a collision objects, which is going to have a bunch of surfaces. And then he's just gonna say for collision objects, and then for now we call each collision object the ground so that we don't have to rename any of the variables below. Look at this. Okay. Oh, that's sick. Wait, that actually kind of works. Okay, so let's draw all of the languages now. Can't the LSP do that? Yeah, but it needs a name to reference first. So now we can call this obj, and then it will fix it all. But you need to start with it working. You know. Okay. So in our index JavaScript, now we just go over we don't have this ground thing. We have here for simulation state collision objects, and then it's probably obj of, not in, would be my guess. I think I can never remember the difference between the two, but I just know that one of them works and one of them doesn't. And then here we replace all references to ground with obj. Okay, and then let's let the simulation run for a little longer. So here we had our reset after 1 second. Let's reset it after 3. Oh, yeah, nice. So here, it's falling through the middle because I actually don't know why. Item of an array or key in object. Oh, I see. So one iterates fields, one iterates items, and then probably there's some sort of like iterator API that you can access if you want to implement of for like any custom type. Okay. So I think what's happening here is that we checked from center towards edge of module. Do we go through? And why is that not working? I was going to say that this, like at the edge, degrades. Oh yeah, because the radius of the ball. No, this shouldn't fall over. This shouldn't fall over. Let's look at the collision check again. Let's look at the collision check again. Move both a little bit up. I don't think that's it. I don't think, because like the ball is not clamped to the screen or anything. So how do we check if they're collided? We say, hey, where does the ball intersect with this line? And if it's greater than the left edge and less than the right edge, we call it collision. So can we maybe look at std debug print a which is a number, b which is a number, and ball, which is, or collision point, which is a number. It's possible that like if the ball normal lines up directly in some way, we fuck up. Like if we're like right above A, then there's like maybe some degenerate math there. Oh, let's see. Obj A x, obj B x, and collision point. Someone's betting that the collision response pushes it through the other wall, but I don't think, I would think that it would push back and forth forever. Okay. Fuck. Maybe we want to log. Surely we should be able to tell when this happens. So it's if the ball pause y is less than ball pause r. That's when we fucked up. Ball radius. That's when we want to look at this. Okay. So here we have 0 to 0.5 and we're just out of bounds, and here we're at 0.5 to 1 and we're again just out of bounds. Interesting. Out of left field question: to ensure that the ball always moves on and not get stuck in a container, shouldn't there be a timeout from when the WASM code in the container is overwritten by some default? What I was thinking for this is that like there's gonna be like some sort of like web interface, like we're gonna have like upload, right? And somebody's going to like stick their WASM module here and click the button. And what I was going to do at that point was run the simulation on that WASM module for some amount of like time, like time boxed time. Like maybe I don't know exactly what I'm going to do, but I wanted to like count instructions. Right? How many instructions did this thing execute? Which is an approximate measure of computational complexity. I know that like some instructions on x86 will run faster than others, whatever, but like just kind of as a ballpark. I want to check its like size, right? So how big is the module? It shouldn't be over some certain size. And if I run the simulation for like n time, how many balls go in and how many balls go out, right? So I can just flood it with balls and make sure that like it keeps all of those things in state, and I'll just reject any modules that don't satisfy all three of these constraints. That's kind of what I was thinking. We'll see how we feel about that later, but that's what I was thinking. And I think it's reasonable to bring up these questions ahead of time because it's fun. It's good to like think about them before we get there. I guess we kind of want this to be like less than or equal to ball r plus 0.01 or something, and ball pause y is less than, greater than ball r minus 0.01. Then we should only see logs when it like really gets fucked. Okay. So yeah, it does look like it's just slightly out of bounds. But I just don't understand why that would be. Because the center point of this thing, right? Like if I have wall like this and ball like this, how would this ever miss? You know? Unless I've done something stupid, like checked this point on the ball instead of this point on the ball. That seems possible. Because then it would miss. So can I log the collision point just like overall? Let's do that. And we don't need to log these. Yeah, wall balls. Fuck it. Oops. We can't log this as a number anymore. We have to log this as anything. And okay. So in this case here, we are at how hard can it be to answer will this halt in a reasonable amount of time anyways? I kind of imagine that if I just fucking run it in a thread with perf and then kill the thread, that should be good enough. Right? Assuming that with perf, like assuming that ahead of time compilation of the WASM module results in something that perf can instruction count effectively. Maybe perf is the wrong example, but I'm sure there has to be some tool on Linux to like measure instruction count. Valgrind for sure, right? So I'm imagining that'll be good enough, right? Where reasonable amount of time is just by instruction count, but maybe not. Okay, so the collision point, maybe this isn't what I want to log. I want it to log where on the ball, where relative to the ball we're looking at. So collision resolution vector is the ground normal multiplied by the collision resolution distance. I guess I want that because we add that to the ball position. Let's look at that. Resolution vec is an any, and we'll just put this guy in here as well. Collision resolution vec. Okay, So in the case where we're looking at the left wall, we are looking at the ball up in Y, odd, left in X. No, right in X. Oh, it's just the wrong side of the fucking ball. It's just the wrong side of the fucking ball. We need to negate this. Because we were going away from the wall instead of towards it. So we were just fucking dumb shits. No. Whoa, 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 whoa. Why does that not work at all anymore? Because he's actually now going. Oh, what the fuck? So he's doing something just brain dead here. Collision resolution vector. So this says I see. No, I don't see. I do not see. So collision resolution distance is the ball A minus the ball collision point. Ball collision point is add the ground normal times negative ball R. But I guess we just need to do positive ball R. Then does everything else kind of work out? No, there's going to be some like fucking bullshit that happens because of that as well. No, it's not using the wrong side. That's making it use the wrong side. So this was correct, right? It's bouncing. It's for sure hitting on the right side. Okay, let's slow down the simulation. That will, like, why the fuck didn't we do that, like, immediately? 10x slowdown, please. Right, so here, it's definitely colliding at the right spot. Here. You're saying somewhere I want an abs instead of a sine flip? That could be it. I want to push. Yeah, I could maybe see that. Let's see what happens when it gets here. This is a bad way to test this. We could... Okay. I guess this doesn't give us any extra information from before. We could have just run at full speed to get there. Collision resolution vector. When we are looking at the left... Oh, this is the right wall. No, A, B. A0, B 0.5, this is the left wall, because these are x positions. Here, the collision resolution would be up and to the right, which is correct. Yes. Up and to the right. So that's fine. Then the collision point is just a little bit over 5. So this is what I'm not understanding. It feels like collision point is wrong. Oh, but I guess it could be... Yeah, there is nowhere in this entire cone where it should ever be out of bounds of this line. I think. Pretty sure. So the collision resolution point must be wrong. So here we take the ball position and we add the collision resolution vector. Let's think about that. Ball, line, intersect. This is wrong. Because we're adding from the center of the ball instead of where? The ball collision point. This feels more correct? That could be it. We don't need to go fucking 10x slowdown. That's fucking annoying. It's annoying. Refresh. Fuck. I'm wrong again, baby. Wrong again. So the ball line intersection point, ball collision point is the ball pause. Oh, this is ball collision point rel center. Okay. So here we are. Oh no, this is just the absolute ball collision point. Then here, our ball line intersection point is the ball collision point in absolute space with the resolution vector. Okay. So in our failure case, the collision resolution vector is going up and to the right, which we think is correct. And the ball intersection point is just like, hey, I'm too far to the right. Oh, wait, I think I see it. So we have the ball here. It moves some amount down, right? To here. Then the collision resolution goes here. And so it's out of bounds. I'm pretty sure that's it. So our collision resolution point, maybe instead of being pushed out here, should be here. Does that make more sense? We just undo any action and then apply the velocity change relative to this vector, which isn't perfect, but I think it's more perfect than what we have right now. More good enough. Ball line intersection point is, okay, let's think about this. Let's just double check that's right. So we say we have the ball's current position after velocity is applied. Yes, after we've done our movement. After we've done our movement, we just add the ground normal to the ball position to get this point in absolute space. Sorry. Yes, this point in absolute space. Then we say that the collision resolution is to go this way, which is not what we want now. We want it to be this. So let's just double check. We use this here, but then we also use this collision resolution vector twice. We use it down here to push the ball back out, which is not what we want now. We want both of these things. So we're going to say, I think we can still use that actually. We just have to check if the ball collided first. Yeah. Let's say, okay, so before we were doing this, ball, go through wall. We say, hey, we need to go this far to get back in. Just fucking double that distance, right? And so I think what I'm going to do instead is from here, apply this. That's probably good enough, close enough. That seems reasonable to me. That seems reasonable. So this is the collision resolution distance. We check the ball intersection point. All we need to do here is find this instead, which is something to do with like the ball's initial velocity. How are we doing this before? We dot product when we had a ball normal. We did this projection. And now, instead, we just want, instead of normal, we just want ball velocity. Yes. Then we know how far backwards to go on the velocity path. So this, instead of dotting with the ground normal, we say const backtrack distance is this same thing, but dot ball velocity. And this is probably negative. Oopsies. Fuck. Yeah, okay, we can try that. We can try that. Then we set the ball position to the ball position minus added with the backtrack distance multiplied by the velocity. Uh-huh. And then we add from here the collision resolution vector. Let's see what that does. Surely I fucked up something. I fucked up some sign somewhere, probably. Yeah, just immediately, just what the fuck is going on? So backtrack distance, let's just double check this here. So the A position of the line, the distance between A and the ball collision point, that's this line, that's fine. Dot producted with its velocity. So its velocity is down. Okay, let's say that's like a little bit off down. This is that projection. Let's think about this. This. Oh, this doesn't work anymore. We can't dot product this way. Because the only reason the dot product worked was because the normal vector was like orthogonal to this line. So we were getting the hypotenuse of this, and this was like this. But that's just not true anymore. So to find the intersection point between the ball and the line, we need to do we go back to this like line intersection test? Where we yeah, I think that we just have to go, we'll just go back to line intersection. I think that's fine. That is fine. So did we do this line intersection anywhere? I don't think we did. I don't think we did. Unless somebody has some linear algebra bullshit that makes this easier, but I don't think it does. I don't think there is. So velocity, surface, point. So here's A, B. We need to know how far back we were at this point. So there is some triangle here where it has like X and Y coordinates. But yeah, I think we just have to do the intersection. We just do have to do the intersection check. So function line intersection point is well, I guess we'll use surfaces here. Surface. No, we can't. We want to use just maybe. No, we should use surfaces. Surfaces make sense. We'll have to adjust this later. We'll call the surface something else, but the surface does have the points that I want. And this is going to return back a pos 2. And so we have line 1 is mx plus b. And line 2 is nx plus c. So then we rearrange this to be x is equal to, if these two things are equal, we have x is equal to c minus b over m minus n. And so now we just have to convert these surfaces into this representation. So I guess we'll just do this. We'll say function line params returns some like line params. Const line params is a struct, and he's got a slope and a offset. The slope is by minus ay over bx minus ax. Yep. Should be self dot everywhere. Yep. And then what's the offset here? It's just wherever x equals 0. Yeah. So we plug in. No, we just say a, the point at a is equal to slope plus slope times a dot x plus b. A dot y is this. Yeah. So then to go backwards, we say b is equal to a dot y minus slope times a dot x. Yeah. Self a y minus slope times self a x. Good enough. Good enough. Dot a slope is equal to slope. Dot offs is equal to offs. Boom, boom. So now we can go back here and we can say const a params is equal to a line params, b params equal to b line params. Then we say x const x intersection point is b dot b params offset minus a params offset over a params slope minus b params slope. Distance from ball to intersection might be more interesting. Find the closest intersection, move the ball that distance minus some small delta, apply velocity response, and try to move the ball. Isn't that what I'm doing? I think that's what I'm doing. I think, but we'll see. We will see. I'm pretty sure that's what I'm trying to do. I'm just maybe getting there in a bit of a roundabout way. That happens a lot. Okay, so the y intersection point is just like a params slope times x intersection point plus a params offs. Then we just return x equal x intersection point dot y is equal to y intersection point. Okay. So now we should be able to find where we intersected by looking at the intersection point is going to be the ball collision point. Okay, so we need to like create some line that is like where that point moved through. So we have the ball collision point. This is B. So this is a ball collision movement. This is a surface, which is kind of a fix me, don't call this a surface. But his B position is something. I guess this is just the point right now. And then his A position is somewhere as well. It's just a ball collision point at ball velocity. Yeah. That sounds right. Here we are not doing like any clamping between the lines, which is maybe kind of fucking stupid, but that's fine. Maybe we'll look at this thing in terms of surface line params. That makes more sense to me. Yeah. So we have some line parameters that define some line. Which means that here we can just use A and B instead of A params and B params. Boom, boom. Here, boom. Yes. That makes sense. That makes sense to me. Then we can say that we have ball collision point movement. This makes sense still. Is this surface with this movement? We get line params out of it. Yeah, seems fine. I don't know why it doesn't like this. Like, this should be fine. I guess maybe in Zig you can't do this. So we'll just call this ball collision point movement line params. Okay, fine. So we have that, and then we have the line params of the object. So const obj line params is equal to obj line params. Then we should be able to say line intersection point ball collision point movement params obj line params. This seems reasonable. Yes. Yes. Const intersection point. Yeah. Backtrack distance goes away. Then this just becomes intersection point, add the resolution vector, which still is fine. And then we just have to check our collided thing is now going to be our... Oh, we already have this. Ball line intersection point. And we just don't calculate this here. Yeah, and we don't have to log this either. Maybe. Let's see what that does. Let's see what that does. Could do something. No field offset in line params. Why? Is it offs? It is. Fine. So he's just falling right through. So clearly we're fucking stupid. Okay. Can we look at the std debug print ball line intersection point? And maybe we look at the ball pause as well. Let's just see what the fuck is it doing. What the fuck we do? Oh, fuck me. Fuck me. We need new lines. New lines. Ah! Okay. Can we reset the simulation more? Or maybe run the simulation at slow? So that we can stop it when it hits the point we care about? Refresh. Okay. And now. Perfect. Okay. So we have the ball position is here. The ball line intersection point is not number, not number. So we just are idiots. Ball line intersection point. Not a number, not a number. So let's just double check we got this right. So here, that's going to happen if B slope and A slope are very, very similar. So can we maybe... I guess probably it makes more sense at this point to GDB this. So GDB Zig, build, and GDB are Zig out this. Break here, run. So can we look at the obj line params? Slope is negative 1.2. That makes sense. Ball collision point movement params. This is just fucked up. Okay. So where does this come from? This comes from the line params. P ball collision point movement. So here the x just did not move, which makes sense. Okay, yeah. So we're doing y over x to find the slope of the movement, and the movement is totally vertical, and we just like are degenerate there. It's just falling after all. Yeah, it makes a lot of sense. Makes a lot of sense. So we just have to handle that case. Is there an easier way to do this instead of by working from velocity? We can just do velocity. We can say that the movement params come from one step before to one step after. Can we like normalize this in some way? I guess we're using like line formula, which is just fucked. And we just have to probably ugh. So I think the easiest thing to do here is just to flip the coordinate system if we're above some threshold, right? I don't know if I'm just like I don't know if I'm going through this in like a really, really roundabout way. I guess we could just look up line intersection instead of just doing this off the dome. Okay, so this is P Q R S. U is where is he just like telling us? Does he have the answer? Ugh. Gross. Gross. What is this guy doing? Returns 1 if the lines intersect, otherwise 0. And then he does. Oh, this is nasty. I don't like this at all. I don't like this at all. This is probably why I did the line things, because I understand the line thing. Line, intersection. Jesus Christ. The point of intersection is d minus c over a minus b. Oh, this is what I did. Given two line equations. Wait, okay. But there's just, we need to like check the degenerate case, I guess. Suppose two lines, blah, blah, blah. Bullshit Lionel G solution. I think it's dot n p minus a over dot n norm minus v. Dot. So n here would be normal, but we're not working with the normal. But I guess you could kind of view the velocity as the normal in some way. Surface velocity. So this is the surface normal here. And is there some way that this plays in? Here. Oh, fuck. Can you just project the normal onto the velocity vector? Yeah, that seems right. Project normal onto a velocity vector. And that's it? Oh, you need some sort of like scale from somewhere. Which you're saying you're getting from like P minus A. So this is A, this is P. Well, let's draw it a little differently. You're saying A. Let's just draw this as like here. P. You're saying that you have dot normal over P minus A. So this is P minus A. And so if you project this onto the normal, you get this distance. No. You get this distance. Yes. Okay, so you're saying you have this divided by the dot product of the normal over the normalized velocity vector. So the normalized velocity vector in this case is like this. Yeah, I'm not really seeing it. I'm not seeing it. I'm not seeing it, but maybe that's just because I'm a dumbass. Oh, it's because this line is this line. Ah! I see. No, wait. Does that make sense? I think that does make sense. I think that makes sense. I will trust it because what I tried to do didn't work. And so I think that makes sense. I think that makes sense. Thank you. Thank you, thank you, thank you. So here we're just trying to find ball line intersection point, and we can just do ball. So it's like this ball collision point dot ground normal, except this is going to be the other way now. So this would be ground normal dot with this shit divided by ground normal dot ball velocity length. So ball velocity mol 1 over the length. Yes, yes. And this is ball line intersection point, and then probably I think this has to be negative. We can try it. It'd be cool if that worked. I think based off the drawing, it feels like it works, but oh, and then this needs to be multiplied by the direction of the velocity. So this is ball velocity mol. And then I'm just gonna say VOD 0152. This is how I'll track it back. This is how I'll track it back. Okay. Because later I'm gonna have to fix this. So 265. Oops, ball, pause, add this. There you go. In the direction of negative velocity, no? I think I got the negative in there, but I could have missed it. It looks like it's good. Looks like it's good. And does this fix the fact that it falls to the ground? Let's go, baby! Let's go! We did it. Reddit, we found the Boston bomber. Were you guys, was that like an old enough reference that people don't get it anymore, or is it still funny? The time where, what year was that? Boston bomber. 2013. So in 2013, there was like a bomb that went off at some marathon in Boston, and Reddit went through all of the photos from like all sorts of security cameras and people's phones and stuff, and they found the guy, except they just found some other guy. So like they were so confident, and it was like a big deal. Everyone was like, we did it, we found him. And then it was just not him, which is just really funny. That's such a fucking classic Reddit maneuver. Such a classic Reddit maneuver. Okay, let's make this faster again. And let's just see if this feels okay. We're running under GB. Fuck that noise. What the fuck happened? Wasn't this, didn't it look like it worked when we tried this before? No. I thought that it looked like it worked. Maybe it was because the time step was so much smaller. maybe that was like relevant to why it worked. So we'll just make our simulation have a lot more things in it. No, I don't know why. It felt like it worked a second ago. Like, right? Like, before, when I did this, was it not working? I must have fucked something up. I thought I could have sworn it worked. Maybe I just didn't refresh correctly. Okay, let's double check all of this. So ball velocity, so ground normal. Okay, let's take all this out. Oh, fuck. Okay. So what is this? Ground normal dot a sub. Okay, let's like take this out. So this is const a to p. AP we'll call it. A sub ball collision point. And that's this. Then we dot product that onto the normal onto that. So that's this distance here. How did I justify this before? How did I justify this? Normal onto this. That's this distance. Then we did that dot n. Okay, I'm just going to copy this guy's words because I think it makes sense. So this is the normal dot product onto this line segment here. Then we divided that by the dot product of the normal onto the normalized velocity. So velocity is like this downwards thing, which is right. It was like a ratio thing. Yes. Okay. I'm not sure. I think it makes sense anymore, but we will see. So this is mol AP. This is. I've missed something. Ground normal dot. Ground normal dot AP. I guess you did ball collision point sub obj a. Sure. I've probably had an extra negative somewhere. Divided by ground normal dot, we'll call this const v norm is equal to ball velocity multiplied by 1.0 over ball velocity length, which makes this 1 over, we'll call this v norm neg. Okay, so this is const ball intersection dist, and we have to multiply the velocity by that distance. But this velocity should be the norm version. Yeah. So velocity norm this, and then the norm is the negative version times -1. And maybe we should do it the other way. No, that's fine. Doesn't fucking matter. Doesn't fucking matter. So now we say v norm multiplied by the ball intersection distance added to the ball collision point. That feels right. That feels right. Let's see how stupid that looks. Nope. Pretty clearly wrong. Pretty clearly wrong. Oh, yo, 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 yo. My poor little brain. I drew it with a horizontal line and non-45 degree velocity when it worked out. Easier to spot triangles. I feel like the non-horizontal line makes it clear where the velocity ends up. God damn it. My poor little brain. It just feels like it should be so easy. So we're trying to find this distance. And we basically just have to break this down into 90-degree things. So this here is some obvious 90s. Obvious 90s here. Gotta crank those. This is also obvious 90s. So you project AP onto the normal. You get this. And then you can project the normal onto this guy, and then you just need to find this extra bit here. Wait, are these guaranteed to be the same length? Am I high for thinking that? Why do I think that? Oh, but this A is any arbitrary point on this line. So no, those are not going to be the same. This could be equally the problem. Let's draw it like that so I don't get confused. Okay. So how do I find this last distance here? This last distance. Do I have any of I have this distance and this one, which gives me this. What am I missing? There was something about like this dot product stuff that made it feel like it made sense. There's like some vector here. Does that help us at all? No, this is just the same fucking triangle. I'm not seeing it. I'm not seeing it. All right, maybe we call it and we just say Lionel G line intersection. Like, can I just copy a formula from somewhere? Is it time to give up? Line intersection dot products. Line intersection point. Jesus, why is it so slow? Line intersection point dot product. Oh my god, why is my computer just like fucking blowing its like shit? I can't click on anything. Oh my lord. Bump 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 bump. Bump 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 bump. Sorry, I'm just trying to see if I can like think it out in a way that doesn't like make me want to shoot myself. Velocity line. I feel like I just want to go back to like the line formulas because like I could reason about those so much easier. But it just feels like there should be something here. Normal. So I know where A is, I know where B is, which means that I know fuck, what just happened? I know where the start of the line is, I know where the end of the line is. Line. I have normals here and here. Those can help me in some way, shape, or form. Velocity. Boom. Okay. Ah, my poor little brain. We have normal here. We do not know this point. We know this point. This guy drew it out for me because I'm too fucking stupid and slow. Thank you. So A, where's P? V. So P is here. This distance is the dot product of the normal onto P minus A. I agree with that. So far, so good. So you have this. Velocity is coming here. Uh-huh. Then you have dot normal onto this, gives you this angle. Ah, okay. And then you're just saying to the surface along the surface dot n over norm v. So this is the normal vector scaled by the angle in some way. Oh, dot n over nv is just the cos theta. Right. So cos theta is this, which is this distance here, which is how far I need to get back to the surface. Yep, you're right. You're right. You are right. Thank you. You got me there. Man, it's so sick when strangers on the internet just watch me struggle and then give me the answer. That's awesome. So PA is this, ball collision point minus object A. We dot product ground normal dotted onto PA divided by the dot product ground normal dotted with negative normalized V. Let's make sure I got normalized V right. Negative normalized V is -1 over the ball velocity length. So this should give me normalized that. That makes sense to me. Which makes this feel correct, and I just have to apply that to here. That is what this is giving me, right? N over cosine theta. AB is the line, N is the normal vector. I'm trying to figure out this distance. Okay. I think I'm getting lost on this division again. This is cos theta, which is this angle. So this is the projection of the normal onto here, this distance, divided by cos theta. Oh, yeah, because this times cos theta gives me that distance, of course. Yeah. Oh, I see it. And then since my velocity vector is going, did I just get like something like this wrong? Seems possible. Let's see if we can like analyze how this thing is fucking up. Where is it? Do I lose it? Localhost 8000 index. So here he goes, womp. That was obviously stupid. What am I doing wrong here? Okay, so this guy, he comes down and he goes, he's shooting like immediately down this way. I've got like a 90-degree off problem, I feel like. I mean, somewhere it just feels like I have like, maybe it makes sense for when we're in collision to pause. That's what we should do. Here, we will just GDB. Break here. Run. And now we'll see it immediately on our first collision here. We'll see what the fuck we're doing wrong. Info locals. Okay, so we collided. That's a reasonable assumption here. We have the ground normal is up and to the right. Great. Collision resolution distance is some positive number. And the ball intersection distance is some small number, and the collision point is x 2.5, y 2.7. Feels fine as well. Velocity adjustment is probably the problem here. The fact that there's a nan in velocity adjustment, which was coming from the velocity ground projection magnitude, which is the ball velocity dotted with the ground normal. Wait, so that's fine, is it not? Why is this? Oh, we haven't got there yet. That's why. There we go. Okay. Info locals. Except I just lost the ball velocity. Fuck. We run it again. Run. Refresh, refresh, refresh. Okay. Next. Next. So this is where we want to log. And then list. List to 50. Okay. So the ball intersection point should be down and to the left of the ball position. 0.3, y is 0.28, and we have the ball intersection point at a little bit to the left, which is good, and a little bit down, also good. So this feels fine. Ball line intersection point. So I actually don't see a problem there. Velocity adjustment seems fucked to me. What is our current ball velocity? Our current velocity is only down. Makes sense. And so he's saying, like, we should go up and to the right, which I feel like also makes sense. We are going up by 2.3, which is not enough, which is kind of odd. So here, something is wrong. What's interesting to me is that the intersection point actually feels right, which is where we were doing all of the changes just now. Ball velocity dot ground normal. So this is the ground normal, up and to the right. The velocity is down here. Okay. Ball velocity is added to the velocity adjustment. The velocity adjustment is from the normal. Velocity ground projection magnitude, which is a bad name. This is normal. Velocity normal projection magnitude. So the ball velocity, down. Ground normal, up. Simple. What do we expect the new velocity to be? It should have the same magnitude as it had before, just in the direction of the normal of the surface. Right? Is that what we think? No, because if it hits a surface that's sloped really far down, it should bounce down and to the right. How did we work this out before? I think that I got lost. So we had like some assumption that we are basically flipping ourselves over the normal. Right, that's what we're trying to do. Which is, here we're projecting the velocity onto the normal. So that's this. Or sorry, it's this distance. Right, and then we were saying that we basically double that distance to get over here. So the ball velocity, the new velocity, should be added by this projection here, times 2. Yeah. Okay. Which is how we got here. What happens in our current version of things? Fuck. Disable BR, run again. Yeah, it's just doing something like stupid. Absolutely brain dead. Okay. I feel like I'm losing my mind. Right? Because we didn't change. I thought we didn't change anything about the velocity adjustment. So here, let's go back to just checking if it's collided, and then changing the velocity. And like only worry about that. Oh, so that's actually fine. Oh, okay. So the velocity change is totally reasonable. And maybe it's this. Ball line intersection point. Let's try that. Refresh. Yeah, so it's me setting the position of this thing is just totally fucking wrong. Okay. That gives us a clue. That gives us a clue. So let's go back into GDB and break on whatever line it was. And we can look again. Okay. What the fuck? It's this right here. Zig, build. Zig, build, and run GDB. Break on that line, run. Okay, there we go. Refresh. Okay, so we now know that our intersection point is fucked. B ball. Ball dot pause. But it doesn't feel that fucked to me, which is why I'm confused. So if I don't adjust my position at all, nothing bad happens? Okay, how many times do I have, like, can I hit continue? Okay, so there we did something, like, it went fucking rapid pace. I wonder if the first, oh, fuck me. Wait, the ball line intersection point is for the bottom left of the ball. And we're setting the center of the ball that place. Fuck me, man. So we actually want to offset, oh, fuck. Const ball collision point offset is this. Then we have the ball collision point is the ball pause add the ball collision point offset. Okay. Then here we need to set the ball to the line intersection point sub or add the ball collision point offset multiplied by negative 1.0. Let's see if that does something more sane. So here we go here. Oh, fuck me. Oh, it was so simple the whole time. It was so simple. Let's see if that fixes the fact that it falls to the fucking floor. Come on, baby. We'll just wait 10 years, but let's see if he gets there. Come on, baby. Let's go! Let's go, baby! Oh my god. We got there. Oh, god, man. Sometimes we're dumb. Math is hard, man. Math is hard. You know? Math is hard, but we got there. Thank you for the guy in chat that was just walking me through pretty basic linear algebra. That was sick. And that is a lot better now. That's sick. Let's let the simulation run for a little longer and get rid of this debug print because I think that's actually slowing down the animation. And let's let it, yeah, we want to let it run for a little bit longer. Just a little bit. Where was it? There is a reset after timeout. We'll just let it run for 5 seconds instead of 3. Yeah, that's not bad at all. That's pretty sick. That's so sick. I'm quite happy with that. Quite happy with that. Maybe just for one more little funsy, since we invested so much time into this, let's when we reset, put the ball somewhere else, because then we get to see it kind of go through all sorts of different scenarios. Am I peeking when I say something? That's very possible. I reinstall or I upgraded yesterday and it like reset some microphone settings, and so I just didn't. I'm not sure I got them all right. So apologies if that's the case. Is there like a random? Is there just like I just want a random int? Or random float. Float. I need to pass in a random. So I need to make a. How do I? Okay. Zig standard library. Let's random. Let's look at maybe it's 0.12. Oh, random. Stood random. So how am I supposed to work with this thing? I init with like some pointer comp time fill function. Like I just want one. How do I just get one? For thread local cryptography, blah blah blah. Be sure to use this, blah blah blah. Oh, do I need to use like one of these types of random things? Yeah, I guess so. How do I think last time I did this, I gave up and just looked at POSIX Linux random. I think there was a way to get like dev urandom, which just felt easier. Yeah. I can just get random bytes into some float. Default PRNG. Ah. And we init with some seed, and that seed I can just get from anywhere. Okay. Thank you. So I can just say const PRNG is stood rand default PRNG, and then here on initialization, we can create a new RNG just seeded with whatever the fuck. It doesn't fucking matter. So here we can just say RNG is stood rand default PRNG init with 0. Who fucking cares? Then here, when we reset, we can just say const self PRNG random float norm F32 probably then they want this and this. Okay, let's see if that does something sane. Let us see. Doesn't look like it. What does float norm give us? Floating point between. Oh, that's not what I want. Float. I just want something between 0 and 1. Yeah, I just want float, not float norm. They didn't mean norm as in normalized. They meant norm as in normally distributed, which makes sense. Oh, that's pretty funny. So here he starts like in collision and just gets like fucked. So we actually want to we want to do a random x position, but set our y position to like 0.7 or something. Just like make sure it's like up there. Ball start y maybe. We'll just leave it. Okay. Oh, oops. Y. No, wait. Yeah, why isn't that working? Why isn't that working? Let's make the simulation run for shorter. I don't really care right now. I just want to get the randomization working. Okay, it is randomized. Okay, cool. Let's run it for 2 seconds. There we go. Okay, well, kind of like maybe we will let that kind of play in the background while we do our outro. It's weird that it feels weighted to the left or something, but that's okay. It doesn't matter. This is what happens when you seed an RNG with 0 and expect things. So, okay. Thanks for watching, guys. We struggled a little day, but we had fun. If you liked what you saw, we stream most days at around 2 o'clock Pacific time. Right now we're working on this like collaborative Rube Goldberg machine, but if you go onto YouTube, there are previous projects organized by playlist. So recently we were working on this video editor. Before that we were working on QR decoder. There's an operating system thing in there, like file system, terminal emulator, what else? 3D engine, neural network. There's stuff in there if you want to go check it out. There is also a GitHub link in the Twitch description. This is up there now. Code for other big projects is up as well. If you're watching on YouTube, there should be a Twitch link in the YouTube description. Swing by and say hi if you feel like it. Like and subscribe, Twitch Prime, all of that stuff. And yeah, I was happy with progress today. We got a little stuck, but that's fine. We had fun. So thanks for watching, and bye YouTube, Twitch, let's figure out who to raid.